After thousands of years shaped by colonial history, many parts of Africa were left with outdated infrastructure. Into this landscape, China introduced a new wave of development in Kenya, bringing advanced technology and modern engineering to build a massive railway system. Elevated tracks now stretch across open savannas, kilometer-long viaducts cross difficult terrain, and modern operating technology, never before seen on such a scale in Africa, became part of the project. Tens of thousands of workers, heavy machinery, and billions of dollars in investment were mobilized to complete the standard gauge railway in just a few years, an ambitious project widely seen as capable of reshaping Kenya's economic future. So how did China build this railway? Why was it willing to invest so heavily in Africa? And what truly lies behind this mega infrastructure project? Let's explore with Mandarin Tech. Before China's involvement, Kenya's railway system was largely a legacy of British colonial rule. The infrastructure had deteriorated over decades, trains operated slowly, and transportation costs from the port of Mombasa into inland East Africa ranked among the highest in the world. Seeing this massive infrastructure gap, China proposed building a modern railway network as part of the Belt and Road Initiative, turning Africa's development needs into a strategic opportunity for itself. In 2014, construction of the standard gauge railway began with a loan of about $3.8 billion from the China Exim Bank. The state-owned China Road and Bridge Corporation was responsible for design, construction, and technology deployment. In less than 3 years, the 480-kilometer Mombasa to Nairobi Railway officially opened in 2017, complete with Chinese locomotives, signaling systems, technical standards, and workforce training programs, transferred alongside the infrastructure. Despite investing billions of dollars, China's interest was not focused on short-term profit, but on long-term strategy. The loans generate financial returns over decades. Chinese companies gain overseas projects while exporting steel, machinery, and railway technology. In other words, China was not simply building a railway, it was building economic influence, supply chains, and geopolitical presence in one of the fastest-growing regions of the world. First, China's top engineers developed the overall concept for the railway and began conducting on-site terrain surveys. Engineers and planning experts carefully analyzed Kenya's landscape to understand the challenges of the route. Using satellite data, aerial survey aircraft, and modern measuring equipment, they identified the most efficient path to reduce construction costs while minimizing environmental impact. In the end, they finalized a railway line stretching 472 kilometers, running from the port of Mombasa to the capital city of Nairobi. Most sections of the line were built as elevated railway structures, ensuring stable foundations and allowing trains to operate safely and continuously across different types of terrain. After the route had been defined, the next challenge was to reshape the terrain along the entire construction corridor. In Kenya's sandy and uneven landscapes, hundreds of bulldozers and grading machines were deployed to cut down high mounds while filling in lower areas. The goal of this stage was to create a stable and balanced surface, strong enough to support heavy construction equipment and the future railway system. Each section of ground was carefully scraped, leveled, and inspected under the supervision of engineering and surveying teams. Specialists continuously measured elevation and slope to ensure the line maintained the required accuracy across dozens of kilometers of natural terrain. Excess soil and sand were transported away from the construction zone by conveyor systems and heavy trucks. This process created a flat construction site, ready for the compaction step. After the bulldozers finished leveling the ground along the railway corridor, the sandy soil still needed further stabilization before construction could continue. Engineers realized that adding controlled moisture to the loose soil would help the sand particles bind together more tightly, forming a denser and more stable base. Using water pipelines and long spraying arms, groundwater was evenly sprayed across the construction site, allowing moisture to gradually penetrate into the layers of soil below. Once the moisture reached the proper level, engineers used a technique called dynamic compaction, where a steel weight weighing tens of tons is suspended from a crane and repeatedly dropped onto the ground. Each impact creates a powerful compressive force that helps the layers of sand and soil below become tightly compacted, forming a more stable foundation. Immediately after that process, heavy rollers began moving back and forth across the surface, compacting the ground to remove air pockets and lock the sand particles together. The deep rumble of the steel drums echoed across the construction area as each pass of the rollers transformed the soft soil into a flat and uniform foundation. By the time the surface dried again under the sunlight, the ground had hardened enough to support the weight of cranes, concrete mixers, and heavy material trucks. After the ground surface had been fully compacted, construction crews began spreading a base layer of soil over the stabilized sand along the railway corridor. Dump trucks continuously unloaded loads of the region's characteristic red soil from Kenya, which bulldozers then pushed and leveled across the construction site. This layer added additional weight to the sand beneath. It was evenly spread and repeatedly compacted with heavy rollers, forming a dense and solid base layer. Once completed, the surface was strong enough to support the weight of concrete beams and columns, weighing up to 40 to 60 tons, which would later be installed along the viaducts and elevated railway sections of the line. On the reinforced and compacted ground, the railway bridge piers gradually began rising along the corridor of the line. These massive concrete columns were positioned about 35 meters apart, with each pier reaching up to 15 meters in height and weighing nearly 90 tons, depending on the terrain and structural load requirements. Across the entire railway route, thousands of concrete piers were constructed, forming long, straight rows stretching across the plains of Kenya. Each pier was cast using slip-form molds and reinforced with high-strength steel to ensure durability against high temperatures, strong winds, and the constant vibrations generated by passing trains. The spacing between the piers was carefully standardized to improve the stability of the viaduct structure and reduce the effects of thermal expansion. From a distance, these endless lines of concrete pillars extended toward the horizon, forming a vast framework of steel and concrete, the structural backbone of a modern railway gradually taking shape across the vast landscapes of East Africa. The next stage involved manufacturing precast concrete box girders, the structural elements that would connect the piers and form the bridge deck for the railway. Inside fabrication yards located near the construction site, steel molds measuring about 30 to 32 meters in length were precisely assembled to cast each girder. Within these molds, old reinforced steel cages and pre-stressing cable systems were carefully positioned before high-strength concrete was poured in and vibrated to remove trapped air bubbles. After the concrete hardened, each bridge girder, weighing between 70 and over 100 tons, was removed from the mold and transported to storage yards. Thousands of these massive girders were produced continuously, ready to be lifted and installed onto the bridge piers to form the elevated railway structure. Once the precast concrete girders were transported to the construction site, the installation of the bridge spans began. Heavy lifting cranes or a launching gantry, a specialized beam installing frame that moves along the bridge piers, were used to lift each concrete girder weighing dozens of tons to heights of several tens of meters. Each girder, measuring about 30 meters in length, was carefully positioned between two bridge piers with extremely high precision, and with tolerances measured in just a few millimeters. Once the girder was placed on the bridge bearings, engineers temporarily secured it before installing the pre-stressing cable system running through the body of the girder. High-strength steel tendons were then tensioned using hydraulic jacks, creating compressive forces that allowed the entire bridge span to behave like a single, continuous, and stable concrete structure. After the tensioning process was completed, a concrete grout or specialized mortar was injected into the cable ducts to protect the steel from corrosion. The next girder was then lifted and installed in the same way, each span gradually linking together like enormous structural chains. In just a few hours, a viaduct section stretching dozens of meters could be completed. As thousands of girders were assembled, the elevated railway slowly took shape, extending across the vast plains of Kenya. Next, the process moves to the rail manufacturing plant, the place where massive steel rails are produced before being transported to the construction site. Inside the facility, heavy steel billets or blooms, each weighing several tons, are stacked in long rows within the raw material storage area. Overhead cranes and automated conveyor systems gradually move these steel blocks toward a large industrial furnace, where temperatures can reach up to 1,200 degrees Celsius. At this stage, the intense heat softens the metal, preparing it for the next step of the process, rolling and shaping the rails. After leaving the furnace, the glowing steel billets move directly into the rolling mill, where the actual shaping of the railway rail begins. At this stage, the steel is still heated to around 1,000 to 1,100 degrees Celsius, making it soft enough to be stretched and formed under enormous pressure. The billets pass through a long series of rolling stands, each equipped with specially designed steel rollers that gradually squeeze and elongate the metal. With every pass through the rollers, the thick rectangular billet becomes longer and thinner, slowly transforming into the recognizable rail profile. The rollers are precisely machined to create the three key parts of a railway rail: the head, which supports the train wheels, the web, the vertical section that distributes the load, and the foot, the wide base that anchors the rail to the sleepers. During this rolling process, the steel can extend from an initial billet just a few meters long into a rail that measures up to 100 meters or more in length. Powerful motors control the speed of the rollers to ensure the metal flows evenly, while sensors continuously monitor temperature and alignment to prevent deformation. Sparks, heat waves, and the thunderous sound of machinery fill the rolling hall as each glowing steel beam is stretched into its final shape. By the time the rail exits the final rolling stand, it has already taken on its precise geometric profile, ready to move into the next stage of controlled cooling and straightening before being cut and prepared for railway installation. After the massive steel rails are manufactured, another critical component is still needed to ensure the stability of the entire railway system: concrete sleepers. These concrete blocks sit directly beneath the rails and are responsible for maintaining the correct spacing between the two rails while transferring the weight of passing trains down to the track foundation. In railway material factories, pre-stressed concrete sleepers are produced by pouring high-strength concrete into steel molds that are about 2.5 meters long. Before the concrete is poured, pre-stressing steel cables are tensioned inside the mold, allowing the hardened concrete to achieve greater load-bearing capacity and improve resistance to cracking. Once the concrete reaches the required strength, the sleepers are removed from the molds and fitted with elastic rail clips, steel base plates, and fastening bolts, components that will firmly secure the rails above. Each sleeper typically weighs around 250 to 300 kilograms and is installed at intervals of about 60 centimeters, meaning that 1 kilometer of railway can require approximately 1,600 to 1,700 sleepers. Their main function is to distribute the weight of trains evenly onto the ballast layer and the subgrade below, while maintaining the precise distance between the two rails. This ensures that trains can operate smoothly, safely and reliably for decades of service. After the concrete sleepers are transported to the construction site, workers begin assembling the steel rails into complete track modules on an assembly platform. Long steel rails, often tens of meters in length, are carefully placed onto the steel base plates already attached to the sleepers. They are then secured using elastic rail clips and anchor bolts, which firmly lock the rails in position. Each assembly typically includes 20 to 25 sleepers, and are forming a completed rail section measuring about 12 to 15 meters in length. Once all the clips and bolts are tightened, the rail sleeper structure becomes a single rigid unit, strong enough to be lifted by cranes. These finished track modules are then lifted and placed directly onto the prepared ballast layer along the railway foundation. This modular installation method allows construction to proceed much faster and with greater precision compared to assembling each individual component directly on site. Once the rail modules have been fully assembled, they are transported to the construction area. At the site, heavy cranes or dedicated track lifting systems raise each rail sleeper section, typically 12 to 15 meters long, off the transport wagon. Workers then carefully guide and position the module so it can be placed precisely onto the prepared concrete bridge deck or track foundation. Each section is aligned with great care to ensure that the distance between the two rails always maintains the standard gauge of 1.435 meters. When two adjacent modules are positioned correctly, the ends of the steel rails are joined using thermite welding or specialized electric welding, creating a seamless connection that reduces vibration and improves the durability of the entire railway line. After the weld is inspected and ground smooth, the rail clips and bolts are tightened onto the sleepers to firmly secure the structure. Additional modules are then installed in the same way, one after another, gradually forming a continuous steel railway line that stretches along the route. And through the entire process I have just described, the railway gradually takes shape through a series of precise and large-scale engineering stages. Thousands of concrete pillars, tens of thousands of sleepers, and hundreds of kilometers of rail have been assembled into a massive system stretching across the plains of Kenya. More than just a construction project, this railway has become a symbol of modern infrastructure connectivity in East Africa. The Mombasa to Nairobi standard gauge railway, stretching about 472 kilometers, began construction in 2014 and was completed after nearly 3 years of construction, with a total cost of approximately $3.8 billion. When the first train finally rolls along the newly completed steel tracks, it marks the result of many years of continuous design, manufacturing, and construction. And if you find massive construction journeys like this fascinating, don't forget to follow the channel to discover more impressive projects and technologies from around the world.